Back, everyone. After this class, who starts their long weekend? Awesome. I'm excited too. I hope you have a fabulous Thanksgiving weekend. Take some time to rest, relax, reflect on what you are thankful for. Maybe get caught up on some practice problems so you are ready to jump back next week, but take some time to have a break as well. I plan to do so too. Okay, so last class, we introduced intermolecular forces. These are not covalent bonds, but these are attractive forces between molecules. And they are responsible for boiling points and melting points and having matter stick together and not everything exist as a gas. We have different types of intermolecular forces, the weakest being the dispersion forces, kind of like the Jell-O jigglers, a slight partial negative charge for a moment, but then it jiggles away. Those are dispersion forces. Then we have, for polar molecules, dipole-dipole interactions. And then our special stronger dipole-dipole, which is called hydrogen bonding. When we have nitrogen, oxygen, or fluorine bonded to hydrogen. The electronegativity difference there is so big that it is called hydrogen bonding, a special strong type of dipole-dipole. Well, water has hydrogen bonding, and it is such a small molecule, but has a very high boiling point because of the strong hydrogen bonding between molecules. And our whole bodies, our whole planet is based around this small molecule. And because of the hydrogen bonding, we have water that exists, that we can go swimming in, that we can drink, and that our bodies are made of. So we know how to draw the Lewis structure of water. We know how to predict the shape, which is bent. And it's bent because oxygen has two non-bonding pairs of electrons. So we have this partial positive or partial negative area where oxygen is with its non-bonding electrons. It's more electronegative than hydrogen. It draws that electron density from hydrogen. So those shared electrons in those covalent bonds, it's hogging some of those, which makes the hydrogens partially positive. One water molecule has 4 regions of electron density and 4 different sites where hydrogen bonding can occur. So the first one is drawn in here. So with the non-bonding pair of electrons on the oxygen circled in red there, it can have a hydrogen bonding interaction with the partially positive hydrogen on an adjacent water molecule. So that is one hydrogen bond between water molecules. We can then draw another water molecule because when we have water, it's not just 1 or 2 water molecules. We have millions, we have moles, we have so many water molecules. So the water molecule with the hydrogen that's partially positive, that's in blue here, it can interact with that second non-bonding pair of electrons, that additional site for hydrogen bonding. Another water molecule. Again, we're in 3D space. It's a little bit difficult to draw 3D space, but we have another interaction with another non-bonding pair of electrons from another oxygen, and then we'll do a green color over here between the final hydrogen site and another non-bonding pair of electrons. So if we want to circle in yellow where all these hydrogen bonding interactions are occurring, one water molecule can have 4 hydrogen bonds, 4 sites where we have attraction between the partial positive and the partial negative. So I have some water molecules here. Here I'm saying this is my oxygen with 2 non-bonding pairs of electrons, a hydrogen and a hydrogen. So this water molecule, this non-bonding pair of electrons can interact with the hydrogen of another water molecule on the right and another water molecule on the left. And then we're in 3-dimensional space. So coming towards you, we have another water molecule with its non-bonding pair of electrons, and going away from you, another water molecule. So we have this huge network of hydrogen bonding, of attraction between these water molecules, which is why water has such a high boiling point. So we started with dispersion forces. This applies to all molecules. So everything can have temporary, instantaneous, partial positive, partial negative, but it's not permanent. Once we have molecules that have a permanent dipole, that means they have polar bonds, and when we consider the vector of the shapes and the electronegativity differences, they have a polar structure. Then we have these stronger dipole-dipole interactions. And then that special type of dipole-dipole, when it's nitrogen, oxygen, or fluorine bonded to hydrogen, we have that hydrogen bonding. But if we wanted to draw this on a scale, you could even put ionic bonding as the very strongest. Because when we get to ionic bonding, we now have full positive charges and full negative charges, as opposed to the partial positive and partial negative and the instantaneous positive and negative in dispersion forces. The boiling points follow suit with the strength of these intermolecular forces. And we're going to see that here. So what is boiling point? Well, something boils when it turns from a liquid into a gas. And we're probably all familiar with water boiling. You put water in the pot, you turn the stove on, it heats up, and once it starts to boil, some of that liquid water is turning into gaseous water. And you can see it condense on the lid, or you can see the steam coming up out of your kettle. Well, for your interest, if you were boiling a pot of water in your kitchen here in London, that water is going to boil when the vapor pressure of the water overcomes the atmospheric pressure of your kitchen or of the air around you. So that's actually the definition of boiling. When the vapor pressure, the water liquid turning into gas, enough of it's turning into gas to increase the pressure to overcome the pressure from the room pushing down on it. So if you were in London, water is going to boil at 100 degrees Celsius. But if you're in the Rocky Mountains, the atmospheric pressure is a lot lower there. The atmospheric pressure is such that you only have to boil water. You only have to bring it up to a temperature of like 85 degrees Celsius to overcome the atmospheric pressure pushing down on it. End result. When something boils, the intermolecular forces between those molecules that was keeping it held together in a liquid state, enough energy has been added to disrupt those intermolecular forces, to pull them apart, and now they can be gas particles and zoom all around. So if we have stronger intermolecular forces, we're going to have to put in more energy. We have to put in more energy from our stove or our campfire or something to heat it up to disrupt those stronger intermolecular forces. So you have to have a higher boiling point to make that happen. So how do we figure that out? Well, we want to consider the types of intermolecular forces and the surface area between those molecules, and then we can predict boiling points from there. So let's look at this problem here. We need to assign boiling points, and we're given 4 numbers to these 4 compounds. Now, first takeaway, do not start memorizing boiling points for every compound. That'd be a terrible waste of brain space. I don't know what the boiling points of these compounds are off the top of my head. Sure, if I worked with them in the lab every day, then I would learn their boiling points. We probably all know the boiling point of water. But these ones, I know everyone does not know these, and I don't know them either. But what we can do is predict their relative strength. We can predict which one would have the weakest intermolecular forces, which one would have the strongest, and then correlate that to the boiling points that are provided. So let's take a look at these 4 molecules, and remember that we're talking about intermolecular forces. So I'm going to draw out a second molecule of each to remind us that it's the attractive forces between molecules that we're actually rating here. So starting with the molecule on the left, 1, 2, 3, 4, 5, so pentane. This one only has carbons and hydrogens, and we know every carbon there every bend and every end of a line, and then it has enough hydrogens to give everything a filled octet. So this one, carbon and hydrogen, those are non-polar bonds. So we have a non-polar molecule, so we only have dispersion forces here. Well, the next one, this is butanol. We have an oxygen to hydrogen covalent bond here. And oxygen to hydrogen is one of those special nitrogen, oxygen, fluorine to hydrogen bonds that allows for hydrogen bonding. So this oxygen here is quite electronegative, making the hydrogen slightly positive so that these can be attracted to one another with hydrogen bonding. Now the next molecule, this one is an aldehyde. We have a carbon with a double bond to oxygen, and then a carbon with a bond to hydrogen. Now a common mistake here is to classify this as hydrogen bonding. But in this molecule with the double bond between carbon and oxygen, we don't have an oxygen-hydrogen bond. We have a carbon-hydrogen and a carbon-oxygen, but not an oxygen-hydrogen. So we do have a partial negative and a partial positive, but not enough that it's hydrogen bonding. So this one is just dipole-dipole interactions. Then our final compound here, we have a carboxylic acid. So we have that carbon double bond to oxygen, which can have dipole-dipole interactions. We have the carbon chain that can have dispersion forces. And then we also have the oxygen to hydrogen bond, which can undergo hydrogen bonding. We usually talk about the strongest type of intermolecular force, so I'm going to classify this as hydrogen bonding. And I'm going to put lots here because it also has the dipole-dipole. It has more sites for that to happen compared to the alcohol, our second molecule. Okay, so we've classified the different types of intermolecular forces that can happen here, and now we want to rank them on strength. So dispersion forces, I'm expecting those to be the weakest. The next strongest between the given options is going to be our dipole-dipole, so I'm going to call that, well, that's going to be strong. And then stronger than dipole-dipole is hydrogen bonding, but we have to distinguish between the alcohol and the carboxylic acid. Both of them have an OH group that can undergo hydrogen bonding, but the carboxylic acid has the OH group and a carbonyl group, that's C double bond O. So we have more hydrogen bonding, more dipole-dipole interactions that can happen with our carboxylic acid. So I'm going to classify this one as 3, stronger than dipole-dipole, and this one as 4 as our strongest because it has even more sites for strong intermolecular forces. So now I'm going to go back to my problem and say, well, what were the boiling points that were supplied to me? The weakest type of interaction, we're going to be able to disrupt that with the lowest amount of energy. So it can be the lowest temperature to be able to disrupt those intermolecular forces. So therefore, 36 degrees Celsius, that's the temperature that I will need to apply to disrupt the intermolecular forces between pentane molecules. The next temperature is 75 degrees Celsius, so I'll give that to my second in strength. The third is 116, and the fourth is 163. And there we go. We didn't have to memorize anything, but we were able to think through the strengths of these intermolecular forces and assign boiling points. So we will leave that up there and go to the next example. So now we need to assign boiling points, and we're given 3 values to these compounds here. Now, all of these compounds have the same molecular formula, C5H12, C5H12, and C5H12. They're all hydrocarbons. So we're expecting them to have the same intermolecular forces. They can only have dispersion forces. They're not polar molecules. So I'd like you to work with the person beside you and answer the question. Well, what is the boiling point then of neopentane? And that's the one in the box there. Chat with the person beside you. How can we make this determination? And 10 more seconds. And 3, 2, and 1. Okay, most going for A, and I agree. That is the lowest temperature. How did we figure that out? They had the same type of intermolecular forces. We couldn't make the distinction between dipole-dipole hydrogen bonding and dispersion forces. Only dispersion forces. But what we can do, and 75% of you, 70%, identified that, what we can make this distinguishing decision on is based on surface area. Here I have my normal pentane molecules. That nice zigzag one. You can see that we have lots of surface area, lots of areas for those jello jiggler electron dispersions to be attracted to one another. That's in contrast to neopentane. On your page, it just looks like an X, but what it actually looks like is this structure. So the central middle carbon has that tetrahedral shape with a methyl group on each one. So they kind of look more like balls or building blocks here. So they have a smaller surface area to be attracted to other similar molecules. So this one has the smallest surface area, and the straight one has the largest surface area, and so this one is going to be in the middle. So the smallest surface area is going to have the least opportunity for interaction with other similar molecules, so it's the easiest to disrupt. We can apply a lower temperature and still get it to boil. So 9 degrees Celsius, the next temperature, 28, and the final, 36. So that is boiling point, and the same principle applies to melting point as well. Melting point, of course, is when we're talking about a solid turning into a liquid. So we still have to disrupt some of those intermolecular forces, but we're not turning them into gases and completely tearing them apart. We don't have to put that much energy in. That's why melting points are lower than boiling points. But we also need to consider the packing, how easy it is for these to stick together in this solid structure that's kind of vibrating in place. We have to input enough energy to break up this solid crystal lattice so that they can start moving and passing over one another like a liquid. How do we figure that out? Well, same principle. We're looking at intermolecular forces, which means we want to look at the type of intermolecular forces and the surface area for attraction. And we can also think about molecule symmetry, but we're not going to get into the details of that in this course. So how well it packs together also impacts melting point. So the trends are going to be very similar to boiling point when we're looking at intermolecular forces. So if we have something that can only have dispersion forces, you can see that melting point is very low. Very cold temperature, we can turn that from a solid into a liquid. Once we have the dipole-dipole interactions with a polar molecule, you can see a big change there. So like 40 degrees Celsius, give or take, change. And then once we get to hydrogen bonding, we can see a change in temperature there as well. More hydrogen bonding. And dipole-dipole. And then we have an extra one here that has a full positive, our sodium, and a full negative. And here we have an ionic compound. So if we're looking at a continuum of these intermolecular forces, once we get to really strong partial positive and partial negative, we get the full positive and negative. And take a look at that melting point. We're at like 300 degrees Celsius. Once we get to the full positive, full negative, we have a very high melting point. And that's why salts and minerals have very high melting points, strong attractive forces that we would need to disrupt, very strong crystal lattices. Okay, so there is our melting point, very similar to boiling point. And now that wraps up topic 3.3. We've taken Lewis structures to Vesper shapes and applied it to the attractive forces between molecules. But now we're continuing on in chapter 3. And the reason for this is because we have a little bit of a conundrum. I'm not sure if you noticed. Hopefully you were distracted enough by all the good chemistry that we were talking about. But you may recall from last week when we talked about electronic configurations in atoms. You know how to write out the electron configuration for carbon. It would be the most recent noble gas, helium, and then we have 2 electrons in s orbitals and 2 electrons in p orbitals. That's how we would write out the electron configuration for a carbon atom by itself. But then once we finished chapter 2, we went on to chapter 3 and talked about how atoms come together and form bonds. And we drew Lewis structures and we looked at shapes and had some fun with that. Well, we now need to reconcile our understanding of Vesper shapes with electronic configurations, because there's a little bit of a problem here that we haven't told you about. If we look at this electron configuration for carbon, if we have atoms in the 2s orbital, or sorry, not atoms, electrons, and in the 2p orbitals, s orbitals are spherical, and p orbitals are orthogonal. So they're 90 degrees apart from one another. Well, if carbon wanted to form a bond and make methane, for example, I'm going to take that paired electron in that orbital and I'm going to put it in the unpaired 2p orbital just so that they can share new electrons with hydrogen and form a molecule. So then I have half-filled orbitals that can become full. If I draw CH4, I would draw it like this. We know that it has 4 regions of electron density, and the bond angles are 109.5 degrees apart. So p orbitals, px, py, pz, are orthogonal. So px, py, pz, they're all 90 degrees apart. When I draw methane, CH4, I don't have anything that's 90 degrees, even though the electrons should be in an s orbital and in 3 orthogonal p orbitals, px, py, pz. So I would expect the electron in the s orbital to be doing whatever it wants, it's in a sphere, whatever, but then 90-degree angles. And we don't have any 90-degree angles here. So where are the electrons from the carbon atom if they're not in s and p orbitals? This is a bit of a conundrum. So we needed another theory to explain why we have a tetrahedral shape, bond angles of 109.5, when p orbitals are 90 degrees apart from one another. So what's happening when bonding occurs? What's happening sometimes when bonding occurs? Well, enter valence bond theory. And again, when we can understand the title, it informs us on what this theory is about. So we're looking at the valence electrons. We know the valence electrons are the ones that participate in bonding. And those valence electrons participate in bonding, and then really they weren't very creative with the name. That's all we got. So it's about valence electrons, and somehow they bond together. This is going to help us figure out how Vesper shapes and electron configurations come together. So some principles here. Covalent bonds are formed by orbital overlap. So what we do is, let's imagine we had a 1s orbital from hydrogen and another hydrogen atom with an electron in a 1s orbital. If we want to form a bond between this hydrogen atom and that hydrogen atom, we bring them in close proximity and the 1s orbitals overlap, and that forms a bond, a single bond. And because the overlap happens between the two nuclei on axes between the nuclei, we call it a sigma bond. So new term that you may remember already. If there is an overlap that happens on axes between two nuclei, that is a sigma bond. So draw the two nuclei. If you draw a line between them and the orbital overlap happens on axes between those two nuclei, it's a sigma bond. Well, that's great. That makes sense for hydrogen. Gets a little tricky when we look at methane. So let's keep going. Electrons are localized. Okay, so the electrons are going to stay in the orbital regions that we would expect them to be in. Okay, and cool new addition with valence bond theory, orbitals can hybridize. That's the cool new thing that we need to figure out. So what is hybrid? Well, you're already familiar with hybridized vehicles. A hybrid vehicle can use gasoline and it can use the energy from a battery. So it takes those two energy sources and it can use both. Or a hybrid dog. I have a golden doodle, so it's a combination of a golden retriever and a poodle, and you end up with the sweetest golden doodle puppy that you can ever imagine, and I have the most wonderful dog at home, and she's a hybrid. Well, we can do the same thing with orbitals. We can take atomic orbitals, s, p, d, atomic orbitals, and we can turn them into hybridized orbitals. And I brought today my magic hybridizer. So right here, I have a magic cup. I hope you can see it. It's very important. A magic cup that is a hybridizer. It can take atomic orbitals and turn them into hybridized orbitals. So let's say I want to take 4 atomic orbitals. I'm going to take an s, px, py, pz. I'm going to take 4 pure atomic orbitals. So s, it's my sphere. I know about that one. My px lies along the x-axis, y-axis, and pz on the z-axis. And I shake it up, and my magic hybridizer turns this into 4 hybridized orbitals. They are the same size, the same shape, the same energy, so they're degenerate, and they look the same. They have like a big lobe, like a big part, and a small lobe. That's in contrast to p orbitals that were like symmetrical. These ones aren't symmetrical. It has a big lobe and a small lobe. I have 4. They're all the same, and we know, and if I had electrons in them, we know that regions of electron density try to get as far apart from one another as possible. So these are going to orient themselves in 3-dimensional space in a tetrahedral arrangement. So let's imagine here, and here, and here, and so on. We have 4 hybridized orbitals that are going to be as far apart from one another as possible, which means they're going to have a tetrahedral arrangement. We put in 4 atomic orbitals. So 4 went into my magic cup, 4 came out of my magic cup, but the ones that came out are hybridized. What are they called? The great reveal. They're called SPPP, but we don't want to say that, SP3. This one's an SP3, this one's an SP3, this one's an SP3, and this one's an SP3. We got 4 SP3 orbitals out of our magic cup. When we draw them in 3-dimensional space, they have a bond angle of 109.5 degrees. These regions of electron density get as far away from one another as possible, so the large lobes are oriented away from one another in a tetrahedral arrangement. That's how we get SP3 hybridized orbitals. The SP3 hybridized orbitals are formed when bonding starts to happen. So for example, going back to carbon, we put in an S, a P, a P, and a P. We got out 4 hybridized orbitals. So this carbon atom now has 4 SP3 orbitals. And if we want to make that methane molecule, which was our conundrum that we started with, we can bring that 1s orbital from hydrogen and bring it into close proximity with the sp3, one of them, there's 4 of them, with 1. It overlaps. Notice that it overlaps on axes between the nuclei of the 2 atoms. Since it overlaps on axes, we call that a sigma bond. So we have 1, 2, 3, 4 sigma bonds holding the 4 hydrogens onto carbon. The sp3 orbitals on carbon are oriented 109.5 degrees apart. If one of these was a non-bonding pair of electrons, we would still have 4 sp3 orbitals, because the non-bonding electrons still need to go in an orbital. But I would take my tetrahedral, hide the non-bonding electrons, and pay attention to what's left. This one's just going to have non-bonding electrons in it. And instead, I'm going to have a trigonal pyramidal shape left. And that would be an example of NH3. So they don't all have to be bonding. Some of them could be non-bonding electrons as well. Okay, so that's how I got sp3. What if I didn't want 4 regions of electron density? What if I only wanted 3 regions of electron density? Well, if I want to get 3 hybridized orbitals out, I need to put 3 atomic orbitals in. 3 in gives me 3 out. So I start with my lowest energy. Into my magic hybridizer, I put my S, my P, and I only wanted to get 3, so I'm going to stop there. And then I shake up my magic hybridizer, and out come 3 hybridized, degenerate orbitals. They have the same shape, they have the same energy, and they're going to orient themselves as far away from one another as possible, which is in a trigonal planar arrangement. So I took my S, I chose 2 of my P's, whatever. That meant that I didn't put in my PZ. That one just stayed as a PZ. And we'll get back to that one later. My result is that I have 3 identical orbitals oriented opposite from one another. What are they called? Well, they're called sp2. And I have 3 of them, 3 sp2 orbitals. When we draw them all, we can see they're oriented as far away from one another as possible. And we know from Vesper theory, that means they're 120 degrees apart, which means it's a trigonal planar electron density arrangement. So all of those could be bonding, and that would give us a trigonal planar molecule. Or if one of them was non-bonding, then we would have a bent structure. But we would still have those 3 hybridized orbitals. Okay, what if we only needed 2 regions of electron density? That means we need 2 hybridized orbitals. Well, I go back to where I started. This is my little hint for you You can remember this as you wish. I like to write out S, P, 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 D, D on my paper. And then I just count in the number of atomic orbitals to match the number of hybridized orbitals that I need out. If I have 2 regions of electron density in my compound, that means my goal is to get 2 hybridized orbitals out. If I want 2 out, working backwards, I need to put 2 in. And I start at S. So I count 1, 2, and I'm going to stop there. I'm just going to put in S and P. So I take my S orbital, my pure atomic orbital. I put in my P, pure atomic orbital. I shake it up, my magic hybridizer, and out comes 2 identical degenerate orbitals. They're going to be as far apart from one another as possible, oriented in that direction, which reminds me of a linear arrangement. The bond angle between these 2 orbitals, notice they have like a big fat lobe and then a small lobe of opposite phase. When we bring them together, it just gets kind of annoying to draw the small oppositely phased piece. So we usually just draw the larger piece, but we need to know it has that other opposite phase. And we can see they're oriented 180 degrees apart. It gives us a linear structure. Now I'm going to go back for a second. Notice that we didn't do anything with our PY, and we didn't do anything with our PZ. They just stayed as PY and PZ. Okay, what if we needed 5 regions of electron density? So perhaps we had a trigonal bipyramidal shape. Well, if I want to get 5 hybridized orbitals out, I need to put 5 hybridized orbitals in. So I write down all my options, S, P, 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 D, D. That's as big as it's going to get. So if I need 5 hybridized orbitals, I'm going to take 5 atomic orbitals, S, P, 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 and now a D. And I shake it up, and my magic hybridizer, I get 5 degenerate hybridized orbitals. And to get 5 regions as far apart from one another as possible, that is my trigonal bipyramidal shape. So I have an orbital going up and 1 going down, and then I have 3 going out in like a trigonal planar arrangement. What do I call them? Well, I put in an S, P, 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 D. I put in S, 3 Ps, and 1 D. Out, I get 5 sp3d orbitals. The name's getting longer, but it shows what we put in. They have bond angles, or electron density arrangement angles, of 90 degrees and 120 degrees, just like the trigonal bipyramidal shape. And finally, what if we wanted 6 regions of electron density? We need 6 hybridized orbitals. Well, we need to put 6 atomic orbitals in. 1, 2, 3, 4, 5, 6. I put them all in. S, P, 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 D. We shake them up, and lo and behold, out we get 6 degenerate identical orbitals. We orient them as far away from one another as possible, and lo and behold, that gives us an octahedral shape. The angles between these hybridized orbitals are all 90 degrees. They're all pointing away from one another at 90 degrees. If we have 6 regions of electron density, that means we have sp3d2 hybridized orbitals. So we can work one way, or we can work the other way. We can go from atomic orbitals in to hybridized, or start with our hybridized orbitals, or even with our electron geometry and work backwards. If we need 2 regions of electron density, how do we get that? Well, we put in 2 atomic orbitals. We get out 2 hybridized orbitals, sp and sp, and that's going to give us a linear electron arrangement. So you could start at any point in this table. You could say I have a structure with a trigonal bipyramidal electron arrangement. What does that mean? Well, 5 regions of electron density tells me these are sp3d hybridized orbitals. So we can go anywhere on this table and predict what we have. Now, one thing I'll point out that is not too big of a deal right now, but it does matter later. You can close your eyes if this is too much jiggling. Notice the sp3 orbitals, the size of the blue versus the orange. This sp3 orbital, it has 25% s character, like spherical, and 75% p character. When we go to sp orbitals, it's like half s and half p character, and that's going to matter later on. Okay, so let's work on this problem here. We want to determine the hybridization of the central atom in PCl3. Now, I've done the first step for you already. The first thing we need to do is start with the Lewis structure. That tells us the number of regions of electron density, and we can count them up. Here we have 1, 2, 3, 4 regions of electron density. Some of them are bonding, and some of them are non-bonding. We don't really care. They all take up electron space. If I have 4 regions of electron density, what are the orbitals for that central atom? Well, I'm going to write out my S, P, 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 D, D, and I'm just going to count to 4. 1, 2, 3, 4. If I want 4 hybridized orbitals out, I put 4 atomic orbitals in, which means I'm going to make sp3 orbitals, and that means I'm going to make 4 of them. So what's the hybridization of the central atom? Well, that central phosphorus atom is sp3 hybridized. And we did that directly from the regions of electron density. We could also figure out the shape. So I take that tetrahedral shape over here that has 4 regions of electron density. And now's the time, if you have really good eyes, you can read really tightly there. What does it say on the prong of your black model? It says sp3, that's right. So if you ever forget, bring your model kit and look, every single one of these has a little etched sp3 label on it. So use that to your advantage. That's in contrast. Oh, I don't think I brought it. You'll notice some of them are labeled sp2, and I think that's it for those. So sp3 tetrahedral, one of them is non-bonding, so we're not going to name the overall shape based on tetrahedral. We're left with a trigonal something, but it's not planar. It doesn't lie on a plane. It's a pyramid, so trigonal pyramidal shape. Okay. Okay, it's Thanksgiving weekend. I have one more iClicker question, but I think I'm going to save that for Monday. So, have a fabulous weekend. Happy Thanksgiving. Get caught up in your practice problems and enjoy your long weekend. Take care.